Welcome to Theory 4's Physics of Sound. This is my presentation about the physics behind different tuning systems, as well as a brief history and, again, brief physics. So let's get into it. So it starts all the way back in the 400 to 300 BC era with Aristotle. Aristotle comes up with a bunch of different sort of thinkings and theories about what sound is. He eventually kind of hypothesizes that it's the vibration of air molecules. He There's no like idea of what molecules are yet. There's kind of just like this thinking of air, and then he abstracts from that there must exist some sort of sound due to the air. Like that's why it's different in sound in water and sound in other stuff. Aristotle was mostly correct that again sound is vibrations of the air. The way they work, your eardrum receives these longitudinal waves, so the physical particles are moving in space. It's a lot different than, say, light, for example, where you have photons oscillating in like every possible direction. So it's kind of interesting that he thinks about it correctly, where it's like this physical mechanical thing. And then he theorizes that frequency determines the speed of propagation, which is not actually correct. So the speed of the particles moving in the air doesn't actually have to do with how quickly they're oscillating, which sounds very counterintuitive, but is actually true. If you think about it, kind of like spin on a baseball, you can be throwing a baseball at some velocity with some spin, right? And the spin doesn't have like a direct effect on the actual forward velocity of the ball. Like they're two completely separate things. If you want, you could also think about it as two like component vectors. So you could think of one being just a ball moving forwards and the other being it moving to the side, which makes like the total speed increase. So maybe that's a little bit less helpful. Galileo finally cements this kind of relationship between frequency and pitch. Frequency is what you actually hear in terms of pitch. So like A440 hertz. Hertz is it's inverse seconds, so like 1/seconds. So I believe it's you hear 400 oscillations in 1 second for that A. And then this French guy who I will not attempt to pronounce, and his yeah, I'm also not going to attempt to pronounce that. It's kind of a text about music, and you can see here this is a like a little graph of where he's pushing on a string to get different intervals, and it's pretty interesting. And here's it kind of written out in actual staff notation. So just or perfect tuning. So this has to do with dividing the octave into small ratios. Um, it's kind of, I've done a bunch of reading. It's kind of similar to Pythagorean tuning, which we'll also talk about. Wait, did we skip? Um, but there are some differences. So here you can see this like monochord thing. What they would do is press on these different little pedals, these different little well frets, more like it, and it would sound different things, just like a guitar. You would hear different pitches. Here I have a little demonstration. So we can see I'll select sine pi of x. So quickly, I did pi in this multiplier here to get rid of stuff here. So everything will just be in integers. So that's not important, but you can see basic sinusoidal wave. So Starts at nothing, goes up, goes down. This is what the particles of air are actually doing in space. They're oscillating like that, but they still also have forward velocity, so it can be a little confusing. Think about it more like if you've ever tied a rope to something and you like kind of move the rope up and down, or those exercise machines where you do exactly that. That's what's physically happening with the air particles. Yeah. Okay. So you can see there's numbers here. So the wavelength is 2. That's from crest to crest, from trough to trough, or from this 0 point to this 0 point. It's important to recognize that when we talk about 0 points, these are different because here it's decreasing and here it's increasing. So we have to look at the two where they're both increasing, going up the slope there. And then frequency, I remember how it's negative seconds. Yeah, so this would be like a time axis, and you just flip. There's a velocity in there too, but oversimplification. Okay, so now we get into harmonics. So 2 is a full octave. So if A is 440, this would be what? This is A80, right? If you see there's 2 little crests per every one of these. So if you look from here to here, there's 1, 2, and there's only one of the red. And this continues for like 4 and 8, as you'll see. See me mousing over there, counting them. Yeah, so see, still preserved in between those 2 points, except this time you have 4, and this would be 2 octaves above your initial pitch, and then this would be 3, and you still have 8. So those occur in like 2n of the original frequency. And then we'll see, I did a little bit of interference. So this is what the 2 waves look like when they overlap. This is what you're physically hearing and experiencing when you listen to a pure octave. And you'll see, I might zoom out here in a second, and you'll kind of be able to see the general shape. But those are 1 octave and 2 octave added. And then those are 1 octave and 2 octaves, and then 1 octave and then 3 octaves. And they all kind of approximate that sine wave. And then this we'll get into later, this factor of 2 to the 1 over 12, that is equal temperament, which we'll get into a little bit later, but you can see how these intervals kind of interact. So this is, I believe, a perfect fourth. You can see the overlay here. It has definite peaks. It looks not super like jagged, if that makes sense, at this kind of macro level. There we go. Okay, and now we're seeing what like a pure half step looks like in conjunction. You can see it gets like much tighter, kind of shorter, bumpier, more destructive interference happening. It doesn't quite reach the same heights as the other one. And then here again, this is using just or Pythagorean tuning. You can see it kind of emulates the the perfect fourth. They look fairly similar, but they're just shifted a little bit. And there we go. Okay, so Pythagorean tuning. So this F, C, G, D, A, E, B, that's our C major scale, but it's constructed in sort of an interesting way. And this is how it was originally thought to be constructed. So the Greeks would take descending fourths, so F to C, descending fourth, and then ascending fifths, C to G, ascending fifth. So essentially plus 7 in set theory land, right? So descending fourths and ascending fifths are actually the same if we generate a clock face, if we think about it here. So F, here, actually, I can doodle for you a little bit. We take our clock here, we have C, then we have F sharp, so this is 0, this is 6, so we're looking for F, which means we'll be right here at 5, 5, 12. 12 minus 5 is indeed 7. And then we look where we start C, and we're going to G, C to 7, 0 to 7, plus 7, a descending fourth is the same as an ascending fifth. Okay, so clear that up there. Get rid of that. Okay, so there was this thing called the Pythagorean comma. It's a dissonant sound when you play two notes together. So we'll also talk about equal temperament and how we split these so-called wolf tones, which relates to this Pythagorean comma. And then we just talked about how just intonation works for one key. Pythagorean tuning. So the way this works is, so if we look at these common musical intervals for just intonation, they're the same for Pythagoras. They were thought to be built using this interesting little pyramid thingy, which had historical significance in Greek culture. But you can see this is him constructing the scale, trying to get the different ratios between these notes. You multiply these things together, you'll see that these are also both squares, which becomes pretty interesting. And we get what is essentially 3 to the 4 over, 2 to the, sixth? Yeah. And that's cool. 3 to the 4th, 4 to the 3. So again, a kind of interesting math thing there. But they're not the same, and there's this weird multiplicative interval. And then remember how in the last slide we had descending fourths, ascending fifths? We can just ascend fifths and then drop octaves, ascend fifths, drop octave, ascend fifth, drop octave, and it should be the same. Except now we're off in a different spot, right? We've just shifted the problem down the line. Brings us to equal temperament. So now we have 12 keys. We've split the Pythagorean comma. So what we've done is we have a full octave like this. And then we split it in half. We split it in half again. Split these halves in halves, and so on and so on and so on. That was how Pythagoras did it. What we did is we looked at this, and we wanted to know, how do we get 10 jumps or 12 jumps here? Like, how do we make everything perfectly fit into this nice, neat octave? So what we did is we took 12 and we took 2. So we want to take double the ratio. So we're getting from one thing to 2. So we get like 2 to the power of something. And we're going to have to multiply it out however many times. And then we'll get log base 2 of 12. And then we figure out, oh, that's right. If we take some number, and we multiply like this, so this is our first frequency. We're trying to find what we can multiply by. Twelve times, because we're multiplying the previous frequency every time we go from note to note. So what can that be? It's this number, 2 to the 1/12, because for here, to get from like C to C sharp, right, you're multiplying by this tiny little number, and then to get to C sharp to D, you're multiplying by that again. You do that 12 times, you get to the octave. There are 4 connections. So the acoustic scale, Lydian dominant, Lydian mixolydian. So this is just, oops, this is just the scale based off of the harmonic series, like applied to music, which does relate to the writing a little bit. We'll go here. So I used all of these in making this. And thank you.